Hello, welcome back to another lecture. This one's about multiple regressions. No, I did not say aggression, I said regressions, despite what you see in the memes there and all of these weaponries. I guess the guy in the middle is looking kind of mellow, but this is about regression, where we are dwelling on the prediction of a particular response variable as a function of multiple predictor variables. Here you see you get something more fancy than a simple straight line curve because it's talking about some sort of curvature with latitude in the response to area for the number of species that might be present in a place. So a multiple regression is simply trying to predict a y from multiple x's. We're going to focus on ordinary least squares versions of this week. We'll start playing around with fancier versions of that in subsequent weeks. So I say here that it's just simply OLS models, but in fact we can extend that to other kinds of regressions, as you might have a hint from an earlier week when we played around with generalized linear models as opposed to ordinary least squares. Okay, so I'm getting ahead of myself. I should emphasize here that we're really talking about a direct extension of a simple bivariate OLS regression like we've played around with already, where instead of just one x, we're using multiple x's to predict a y. It's obviously very related then to an analysis of covariance, where an analysis of covariance has categorical factors predicting a response, plus we're trying to account for something extra that would be a quantitative factor. So it's a mixture of quantitative and categorical predictors in an ANCOVA, right? In a multiple regression, it's very much the same kind of idea, multiple predictors of a y, but we're playing only with quantitative predictors now. So if you think back to that flow chart I showed you earlier in the semester, and it's still available on the web page, you would have this dichotomy between categorical and quantitative predictors. Here we're going for the quantitative ones, all right? Now, this is subject to the same assumptions as we had in ordinary least squares regressions, where we should have normally distributed residuals around our model. We can evaluate that graphically. We can also do it at Shapiro test if we wish. We can expect homogeneous variance along the fitted model, which means that the variation looks about evenly scattered all across the length of the model. And again, we can evaluate that graphically. We should also just remember that we should have more data points than predictors. That wasn't really an issue when we had only one x, but in this case you could get carried away and have lots of predictors, and as you approach the number of data points you have, you're losing degrees of freedom. So we need to have some flexibility to evaluate the variation in the pattern, which means that we need to be as parsimonious as we can, to have as few predictors as we possibly can. And you might get a guess from the word parsimonious that yes, we're going to be working with AICs here. One more point to mention is that we should not have multicollinearity. This multi-syllable word is just simply trying to say that the x's should not be correlated with each other, at least not strongly correlated with each other. So if you have an x1 that's pretty much redundant because it's tightly correlated with an x2, then you might only need one of those. In fact, having multicollinearity causes problems in regression. So we want to try to minimize that, and I'll show you how to do that too. Finally, as I hinted at, multiple regressions are fully consistent with multiple working hypotheses, and thus we can use AIC model selection as a cornerstone of how to decide what is the most parsimonious, the most plausible model. Okay? So if I have an x1 and an x2, or I have an x1 plus x2 in my models, which one is actually doing the best job? I can evaluate that with AIC. Now, here I'm going to diverge a bit from Crawley. You'll see that he talks a lot about model simplification when it comes to these multiple regressions. It's a pretty major emphasis in his book. I'm going to suggest to you that you can use AIC far more simply, far more objectively, in fact, and more simply to arrive at essentially the same answer in most cases. Okay, so let me give you an example to walk through here for the multiple regression analyses. I think maybe the best way to show you how these work, since you've already worked with ordinary least squares regressions, is to follow through an example. I'm going to use the ozone data set that Crawley also works through in his chapter on multiple regressions, And again, remember, again, he's using the model simplification far more than I am. I'm relying much more on AICs. Well, if you don't know much about ozone, here's a brief introduction. At lower atmospheric levels, it's actually an air pollutant that causes respiratory distress. People tend to show up more often in acute care hospitals with respiratory admissions, given that there was some sort of daily maximum ozone level in the day before. A pretty strong relationship there, suggesting that high levels of ozone the day before lead to respiratory distress admissions into hospitals. And as you can tell from that map, it can often be related to certain zones of the country that might be related to car exhaust in high traffic areas like in LA and also San Francisco, the Central Valley there, having fairly high levels. But also in the east, not only because of urban populations, but because ozone is generated when there's a lot of volatile organic carbons and nitrous oxides from car emissions. The volatile organic carbons, interestingly, are often produced by fairly high numbers of trees. So when you have a lot of VOCs in the atmosphere and nitrous oxides, we tend to also get fairly high ozone levels. Now you might be asking yourself, wait a minute, I thought ozone was low and that's causing the problems at the poles. That's true in the troposphere. Here we're talking about at the very low altitudes where people are breathing it in. In fact, then we have relatively high levels of ozone. Okay, so the data set includes these variables. We have solar radiation, temperature, and wind speed as predictors of ozone concentrations. Now, I can tell you, we can hypothesize that an ozone concentration can be a function of each variable alone. Just individually, they might contribute enough and be able to explain ozone concentrations sufficiently. Or we might have an interaction between solar radiation and temperature, because solar radiation is the oxidizing agent. We had photooxidation of VOCs and nitrous oxides to contribute to ozone, and you expect the higher rates of that chemical reaction at higher temperatures. You might think that those two to go together, but not always, because you can have a cool day that's really clear and sunny. You can have higher elevations that can be cooler but still be very clear and sunny. But temperatures can accelerate the rate of chemical reactions, of course. And we might expect that interaction to be discounted a bit by wind speeds. So more wind would essentially dilute out the ozone levels. Notice that I'm hypothesizing specifically a negative sign here for wind, where I'm expecting wind to not be additive but should be reducing the amount of ozone concentrations. That's important detail because we can double check that later, and in fact if this turned out to be a positive coefficient, it would be evidence against this hypothesis, right? Okay, so let's squint at the data patterns, because that's a useful first step when you're looking at multiple regressions, in fact pretty much any analysis, to make sure that we're not going to have to work with the data some way before we start producing our analyses. So here's a simple pairs plot. If you might remember, you just say pairs of the data set, and you get this symmetrical grid where there are mirror images on either side of the diagonal. The ones that are going to make sense to me to look at are here on the bottom row, because ozone is on the y-axis and each of the other variables is on the x-axis, the predictor variables. And so I'm going to focus on that one, where I can see that it looks like kind of a triangular wedge-shaped pattern there that might cause us some problems. These red lines are general additive models, or generalized additive models I should call them. It's a local regression trying to fit within a narrow band what kind of pattern there might be in the data. I don't know that I believe that one very well, because it's a pretty strong wedge shape, and that suggests to me a transformation might be helpful. Here we're looking at a curvature in the line, as is this one, although they're opposite directions, related to the prediction of those variables to ozone. So it's looking to me like maybe a transformation, maybe a log transformation would be helpful. Why do I say that? Because I expect a log transformation to help with a wedge shape like that, and I also expect it to help straighten out the curvatures that we find in both of those trends. Well, I mentioned collinearity or multicollinearity before, and we can evaluate that when we look at the relationships between the predictor variables of radiation, temperature, and wind. So let's see what those look like. That looks pretty flat line to me. There might be a slight bend in there according to the red line, but I don't know. I don't know this is a very obvious pattern. It looks pretty flat. It does look like there's a negative relationship here, so it looks like there's some sort of relationship, some sort of correlation between temperature and wind. And this looks like there maybe is an arch in there, but that's also pretty hard to tell. If it's there, it's consistent with the idea that I expect a an interaction between radiation and temperature. So I think maybe that is something that is supporting my original hypotheses, but I'm not sure that those are showing much of an interaction. Well, I think we can improve this, especially the problems at the bottom in the main axis that we're most interested in, the ozone as it being predicted from the other variables, by working with log of ozone. So I'm expecting, because we have these nonlinear responses, that I can straighten that out by dealing with the log of ozone, and again just repeating the same hypotheses, where log of ozone is a function of each variable by itself, the solar radiation temperature interaction, or that interaction with a discount for the amount of wind there is. So let me take the log of ozone, rerun the pairs command after having added that log of ozone back into my data set. You might remember I used the cbind command to do that real easy. And then if I just say pairs of the data set again, now I've added on the log of ozone column in the middle of that same symmetrical set of graphs. So I'm really going to focus in on here on these three. Why not focus on the other ones? Well, nothing's changed up here. I haven't transformed any of these variables. The x variables remain the same. All I do is transform log of ozone. And so I want to see how this row fits now. If my log of ozone transformation works, these should be more linear than they were. And it looks like that's the case. Those are pretty straightened out. And this one looks like it's more or less flat, maybe a slight arch in there. So I think I'm going to go with log of ozone. It looks like it's helping make linear models work better. And that's essentially what I'm doing. It's a series of linear terms to try to predict ozone. So if I use log of ozone, what I'm doing is saying that specifically I should see that model 1 is just a function of radiation or temperature or wind, and then radiation times wind, or I'm sorry, times temperature, and radiation times temperature plus wind. Okay? Now remember, when we say radiation times, it's actually an asterisk in R. When we say that in R, what we're really saying is it's radiation plus temperature plus the interaction term. This is very much identical, same kind of story as what we saw when we expressed an interaction term in analysis of variance. So we're just going to say radiation times temperature as a shorthand for that full statement that's there in the parentheses. Okay? So here's the R code that I'm using. A package that you would find pretty convenient, I think, for a lot of regressions is this CAR package. We've already used that. BBMLE, as you might have detected, is my favorite way to get AICs. Another one is AIC mod AVG, which may work better for some people. We seem to be having some problems with that for some reason in the computer lab if BBMLE doesn't work for you. The other thing we found, just as a reminder, that maybe you'd have to take out the AICC, the second one there, for some strange reason to get BBMLE work. But hopefully BBMLE is working for you at home, because I think it's a very convenient way to get AICs. So here's my simple models. First I converted ozone into the log 10 of ozone. I call it low ozone. And so I have model 1, 2, 3, 4, 5, just like I explained what they were before. Radiation, temperature, wind, radiation times temperature, and radiation times temperature plus wind. Notice that I'm expecting that to be a negative coefficient, but I'll wait for the output to tell me that. Okay? Then I just simply use that BBMLE package to say, here's the AIC table request, models 1 through 5. I'd like to see the deltas, and I also like to see the weights, because the weight really is the bottom line for the AICs. And so here is that AIC table. I'm not even looking at models yet, notice. I'm just wanting to see what the AICs tell me, and model 5 clearly rises to the top, heads and shoulders way above the next best one, model 4. So, easy winner here in this case. Model 5 is far more plausible than the other models. Well, let me see what model 5 looks like. Here I just simply say summary of a model 5, just like we've been doing. You can see it's very convenient what it looks like, again spelled out. There's the residuals terms, yeah, fine. And notice that it looks like radiation is not significant, nor is the radiation temperature interaction significant, but temperature and wind are driving this. Okay, so it looks like that's not a bad R squared too. It looks like overall the model's working pretty well, but we're not done yet, because we have to evaluate the collinearity, the multicollinearity, I should say, of this model and the terms in the model. So a clue here, this is from the CAR package. The VIF score, which is this variable inflation factor, is a measure of how multicollinear your variables are. And if you get a score of more than 10, that indicates a problem with multicollinearity. And you can see real quickly that radiation is easily above 10, temperature and wind are down below that cutoff, and radiation temperature interaction is easily above 10. So it looks like I have a problem with radiation and radiation temperature multicollinearity. It means that they're correlated with each other. Well, as you might expect when you have radiation and a temperature interaction in there. Okay. So how would I deal with this? Well, let me double check the residuals first too. Okay. Let me see. If I look at the residuals of the model, which is just simply saying plot the model, and out spits our usual residual plots, that doesn't look too bad. There's a little wiggle upwards down at the low end there. But in general, it's not too far from the zeros. It looks fairly flat across there, fairly even left and right, except for that bend up there. I like the normality plot. That's looking pretty good, except for that oddball point number 17 in the data. It looks like there's some sort of a trend here if I take the square root of the positive residuals. The Cook's distance is more or less flatlining here too. There's that 17 oddball out there. So I think for the most part I'm liking this. The problem really is this collinearity issue. So I need to address that because these are clearly indicated as being a problem in the analysis. So how might I do this? Well, I think to go back to the model, what I should be doing is evaluating what to do with these complicated scenarios where I have this interaction and those two are correlated with each other. Well, as Crawley talks about, we should think about model simplification and deal with the most complicated term first that is not significant and remove that. Well, it's easy in this case. I can talk about the interaction term and remove the interaction, include just radiation, and therefore I would be removing the multicollinearity between those two terms, right? If I take out radiation times temperature, there's really nothing to be correlated tightly with radiation anymore. So if I run a simpler model, my model 6 now, it's just those three additive terms, and what I've done is left out the radiation times temperature interaction. Now I'm going to run the AIC again of all the models just to compare my new model to the old ones, and then I can actually look to see how it scores in terms of all the terms inside the model, and I can again evaluate the variable inflation factors. So here's the AIC output. Notice that the AIC weights have changed, but it's still clearly at least exactly three times more plausible than, more likely to be plausible, I should put it that way, than the most plausible, than Model 5. So Model 6 is easily the most plausible model I have there, far more likely to be the most correct model I've got here. And Model 6 output actually is barely changed. I have the same R squared. I've got everything looking pretty similar, but except notice the radiation temperature is gone as it's supposed to be, and now radiation is easily highly significant. Okay, so removing that complicating factor, which was clearly not helping the matter, the interaction term, I'm down to the three independent factors as a simple additive model. And how do my variable inflation factors look? The multicollinearity, looking great. Now every one of these things is well below my worrisome cutoff of 10. I don't have to worry about multicollinearity in this simple additive model. And in fact, the residuals turn out to look pretty much the same. I haven't done too much to the residuals. In fact, that little bend is still there, but I would say it's not too bad for most of the points. It's fairly even across there, and the normality is still looking really good. There is certainly a trend in there, but I think it's relatively minor, and that's still looking fairly flatline too. So especially given the AIC output that tells me that is my most parsimonious model, I'm sticking with Model 6. And so I could conclude that ozone is a function of more solar radiation, warmer temperature, and less wind. Wait a minute, why am I saying less wind? Well, let's go back to the model, because sure enough there is a negative coefficient in there, and that is significantly different from 0, as indicated by this term right in here. So the negative coefficient is suggesting that wind is in fact reducing ozone concentrations, and that hypothesis was correct. All the above variables are highly significant. They're not collinear, and the adjusted R squared in fact didn't really change much when I removed that extra factor in there. In fact, I think it stayed identical. So that extra term, the interaction term, was clearly not contributing anything. Does that make some sense? So I think the bottom lines are multiple regressions are really directly related to an OLS bivariate regression that we were already using. The real big difference here is that I'm evaluating multicollinearity where I didn't have to worry about that before with only one predictor. These are powerful ways to test alternative hypotheses. I can easily identify the ones that are most plausible. I can evaluate the models that are actually confusing the issue by evaluating collinearity, and I can identify some evidence that tests alternative hypotheses. My opinion, anyway, is that this is best handled in that AIC style framework. I think Crawley makes a good point about model simplification, but you can arrive at a parsimonious simple model, I think, very efficiently and in fact objectively if you stick to an AIC style framework. Notice that yes, I did do some model simplification, but another big reason to do that that simplification that Crawley doesn't seem to spend much time on is the fact that I had multicollinearity in that most parsimonious model first that I needed to address and was actually violating the assumptions of that first model. So my model simplification was a way to deal with the assumptions of the models as well. Okay, so those assumptions still matter. We have to think about those multiple predictors as being collinear, being correlated, and that's relatively easy if we think about that VIF command in the car package. It's really quite simple to be able to evaluate those terms that are multicollinear and then remove them as necessary from your models. Okay, so I hope that's a pretty good introduction to multiple regressions. I hope you see how it can work. Notice that I diverged from how Crawley dealt with the same data set, but ended up with the same answer, and I think in a fairly simple, clean, objective way, because I was emphasizing the AIC framework for evaluating multiple hypotheses. All of that, again, remember, assumes that you have clear hypotheses up front, and that is the list that you wish to evaluate, not some sort of fishing expedition. All right, I hope that helps. We're going to be working with these in class, and you'll be working with ANCOVAs, of course, in class as well. And the two really are quite similar. The distinction tends to be mostly whether you have quantitative or categorical and quantitative predictors. All right, talk to you next time. Bye.